Now we're going to get it a little more exciting. Okay, now we're going to let things speed up and slow down. Let's see what that's going to look like here. And now the calculus is going to show up. Here we go. So let's see, we've done stationary, we've done uniform motion, and now we're going to do constant acceleration. Okay, so we're going to call it non-uniform motion. Right, non-uniform motion. Velocity changes. And of course, the classic famous example that was studied in antiquity, such as falling. Trying to figure out why and how something falls was the major focus of science for like 2,000 years, right? So there you go. This thing is speeding up as it goes down. How does that work? And how do you describe it mathematically? Okay. Another way we could show it is you can drop something. You can also just put something on a ramp, right? And just lift one half of the ramp. And then this will start with no velocity, and we'll slowly speed up and get faster, 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 faster. That's all we're talking about now. Something is speeding up or slowing down, okay? All right. So let's think about that one. Let's imagine, so really falling is kind of fast and hard to visualize. So let's go just to our example of Hal here, right? And he was here, and then he was here, and he's getting farther and farther away, right? Because he's speeding up. So we have like no velocity here, and then a little velocity there, and then more velocity here. Oh, I'm doing vectors. Not till next week, like that. Okay, the arrow getting longer indicates that he's speeding up. Does non-uniform motion follow a straight line? Good question. This week it does. Okay, so we're only doing 1D kinematics this week, so everything is in a straight line, except when I pass Hal around. Okay, but yeah, you can have non-uniform motion in 2D and 3D and maybe 4D. Okay, now, this is very important. Let's draw, okay, so we're about to do more graphs. Let's analyze xt, but we're also going to analyze v of t now. Okay, so the graphs are about to get a little more exciting here. So graphs for this motion, here we go. There's t, and there's x. And if we think it started here, and it kind of went up, and here you just have to trust me, we're going to explain it and then derive it later, is it's kind of like a parabola. But at first, it was like this, and it gets faster and faster like that. Right? That's what the position time looks like for something that is speeding up. So what we can now do, we now know enough about graphs and concepts of calculus to draw the velocity time graph. Right? We actually can't draw it mathematically yet, but I think you'll get an idea that what I'm drawing for you is real. Let's see, so another thing about graphs is if I don't say it isn't, this is always the origin. Okay, this is always the origin 0x and 0t, 0v and 0t. I don't label it as the origin every time. Okay. Okay, so at the very beginning, if I want to go here, what is the velocity right there? Okay, what is it? 0. How do you know? It wasn't moving. Well, that's one reason. It wasn't moving. Also, what's the slope right here? Why did I draw it like that? 0. Right? I very carefully drew the slope 0. You're welcome. Not everybody would have done that for you. You know, some people would have. Okay, so it's 0 there, so I'll put a 0 here. But then what's happening to the slope? It's growing. And you can't quite tell, and I probably didn't draw it perfect, but it's growing at a constant rate. So that's supposed to be straight. A straight line is the VT graph for something in uniform, whatever we're calling this, non-uniform. Okay. This example, it's a straight line. You can have all kinds of non-uniform motion, we're going to do all kinds of crazy things. But in 1D, in this example, rolling down the hill, it's a straight line. I don't want to say it's always a straight line. Okay? Okay. So what we've got here is that Hal's velocity increases with time. Right? That's the exciting part. Now the problem, here's the problem. The problem is that the Vx you find depends on the size of delta t. Okay? So say I told you I want to know the velocity when it's right here. okay? You say, okay, well, let's just do a delta t on either side of that, there and there, and say, well, what's the slope between those two lines? And something like that. And you're like, well, no, let's not do that. Let's do the slope. Let's get the delta t smaller. And if you did that, and this were drawn really well, then you would say, oh, it's actually a different slope. Right? You said, oh, maybe that's too far. Let's do these really far lines from each other. And you did them, it'd be a different slope. And you never get the same slope as you vary delta t, right? On the delta t sides, I'll say, and on where you put it. Right? So what do? Right? This took 2,000 years. Humanity took 2,000 years to figure this out. Right? This was like what took so long. Does it have a velocity at a point in time? That's the fundamental question of antiquity. Does it have a velocity at a point, or is it moving? How can it be moving if it's at a point in time? This is it. It seems not so bad now, but you know, we have indoor plumbing and stuff. Solution is make delta t very small. Make delta t very small. And when I say very small, I mean 0. Shrink delta t to 0 to get instantaneous velocity. Delta t goes to 0, and then it leads to, I'm running out of board, instantaneous velocity. Okay, instantaneous velocity. So the problem is that my drawing isn't sharp enough curved here, but maybe you can visualize, and we'll show you another one in a minute. Yeah, I'll show you another one in a minute that'll make this sharper, and you'll be able to see the difference. Okay, but that's the basic idea. So now we're talking about a new kind of velocity, and we're not sort of stressing it as much as most classes do. If we weren't doing this accelerated kinematics, we would be obsessed with the concept of average velocity and speed and instantaneous velocity. And we're sort of glossing over that a little bit, and we're just going to tie it straight to calculus and get on with our lives. Okay? But technically, when you go with a big delta t, that's the average velocity over that delta t. And when you go with a really small instantaneous delta t, that's the instantaneous velocity. Okay? Okay. Let's see. Cool. Okay, so we're going to look at another case that'll be more curvy, and I think we'll illustrate it even better. All right. So we're still basically focused very much on this, concepts and calculus of kinematics. And we're about to do more xt, vt graphs, because we have a new kind of motion. So step aside Hal, and now we have this here. This is a mass on a spring, right? So if I hold it down here, let it go. Ooh, look at that. Mass on a spring. Let's draw it. Here we go. It's connected to something rigid like that. And it's got a spring, and it's got a mass like that. And it's moving up and down. There you go. There's your drawing. So now let's do our kinematics plots for that. Whoa. Well, I guess we're going to plot, what do we put on the horizontal axis? We're doing kinematics. It must be time. We're doing kinematics, yes. What are we going to put on the vertical axis? Well, let's start with position. Can we call this way position? Well, x? Up? X? Yes, you can. It's physics. You probably want to call it y. I don't want to push you too much on the first day. Let's call it y. Okay. So here's the origin, and here's plus y, and here's negative y. Okay. And the origin, we'll say, is the middle of the motion. All right. So the origin is kind of halfway between what looks like up and down. So all we got to do is draw that, and I'll say it's at 0 at time equals 0. Right. So it goes up like this. And it may be a function you've thought about before, right? It's a sign. That's a position. So let's think about the instantaneous velocity a little more. So this is what we defined here. We said as delta t goes to 0, we get the instantaneous velocity. We're going to talk about it a little more here. Normally we'd have a formal calculus definition, but we're just going to kind of talk about it for now. Is the slope, right, of the line tangent to xt curve. Okay? So this is a good way to look at trying to get the velocity the old way. Right? If I wanted to know what is the velocity right here, and I said, but I have to have really big delta t. I'm not good at small delta t's. So I'll put t1 here, and t2 there. Then the one I would calculate wouldn't even be close, right? It's way too much this way. Or, how about even worse? What if I put t1 here? This is t1 and this is t2. There's your slope. Totally wrong. All right? So what this idea is no, you don't do t1 and t2 big. You do it small, which graphically just means you draw a line tangent like that. And there's v instantaneous, which we'll just call v. We don't put instantaneous on it all the time at that point, like that. Okay? So that's what I mean by a line tangent to the curve xt graph. If you wanted to have it here, what is its velocity here? Instantaneous velocity there is 0. No slope. You mean it actually stops at the bottom? Oh yeah, it does. Watch it. It stopped right now. And now. It stops at the bottom before it goes back up. Okay? So that's interesting. Maybe we're actually smart enough to maybe we're smart enough to now plot the velocity, right? So we plotted the position. Now let's do another velocity graph like this. So here we are doing the graphs. Graphs are very important. So let's look at this. What is the velocity here? Is it positive, negative, or 0? It's positive, right? We have a positive slope there. If I drew my tangent line like that, positive slope. Okay, so it's going to start here. And by the time it gets to here, what is it? 0. It's positive, it's decreasing towards 0, right there, like that. And then after this point, what is the slope now? It's negative. So the velocity is negative. This is when it's going down, right? Like that. Like this. Right? And then it had its maximum here. Its maximum slope is here. So the maximum negative velocity is here, right? The maximum negative slope there, maximum negative velocity. And by the time you get to here, the velocity is 0 again. Well, that's when it comes back out to here. Oh, okay. And then it goes like this. Right? And then it goes like that. So this is the velocity time curve. So you could draw it just by, looking at the slope of the top curve and copying it down. It helps to know what the answer is. It's a little bit easier. So the instantaneous velocity is the slope of the line tangent to xt at a point in time. So that's what we plotted here. Okay. So now when we write this, if we want to write v instantaneous, soon we'll drop the x's and the instantaneous and just call it the velocity, but we'll keep writing it there. We could say, well, it's delta x over delta t, but that's if we let t go really small, we give it a special name, dx dt. Right? So instead of deltas, we put d's. Okay? We get rid of the Greek stuff there and just call it a d. And this is the famous derivative. Right? This is the derivative of x with respect to t. WRT means with respect to in my world. Okay.